NMOS logic with depletion load transistors. Depletion load transistors. The pseudo NMOS gates we have just described were actually based on an earlier type of logic where n-channel depletion transistors were used as loads. This logic family was called NMOS logic and was prevalent in the early days of 8-bit microprocessors. Now it is seldom used. NMOS logic is very similar to pseudo NMOS logic, although historically it came second. Pseudo NMOS logic was described first because it is currently used sometimes for critical circuits in an IC where depletion load NMOS logic is almost never used now. Also, the analysis of pseudo NMOS logic for the gain at the gate threshold voltage is simpler than for traditional NMOS logic, where a second order effect called body effect becomes dominant. This session should be considered optional for a first level course. It has been included because of its historical importance and has an important and as an example of using depletion transistors. An example for NMOS depletion load inverter is shown in figure. The load is realized by a depletion transistor having its gate connected to source. Since for depletion transistors we have VTD less than 0, where VTD is the threshold voltage for the transistor. A channel is present for VGS is equal to 0, VGS is equal to 0. The depletion transistor will be active region for VDS greater than VEFF minus V is equal to minus VTD, which might be on the order of 2 volts or a little larger assuming this to be the case. We have the drain current of the depletion load transistor given by ID minus 2 equal to nu and C naught X by 2 into W by L2 V square dt. Thus the depletion transistor with its gate connected to its source approximation a DC current source ignoring second order effects. As such, it is an extremely efficient realization. In reality, it approximates only a moderate quality current source. A major source of error is that as the source to substrate voltage changes, the depletion region between the channel and the substrate changes, which in turn causes the threshold voltage to change according to the equation. VDT is equals to VTD is equals to VTD minus 0 plus gamma into root over VSB plus mod 2 phi f minus root over mod 2 phi f. This effect is called the body effect. When the inverter output voltage is around the gate threshold voltage, this causes the output impedance of the inverter to be finite, perhaps on the order of only 8 times greater than 1 by Gm minus 2, where Gm minus 2 is the transconductance of the depletion transistor. In addition, the finite output impedance of the depletion and driver transistors also inverter of figure at its threshold voltage to be given by V out by Vn equal to AVn is equal to minus Gm1 by Gs minus 2 plus Gv plus Gds minus 1 plus Gds minus 2 when the output voltage is around the gate threshold voltage. Note that that Gs minus 2 is the body effect transconductance parameter and that Gds minus 1 and Gds minus 2 are the drain source admittances of Q1 and Q2 respectively. The derivation is left as exercise for interested reader. C. Thus, the gain of the inverter at the gate threshold voltage might be between minus 6 and minus 9. However, somewhat low gain has little impact on digital circuits. A typical transfer curve of an NMOS inverter obtained using SPICE is shown in figure. A value of VTD is equal to minus 2 volts was used to obtain this curve. Also, the W by L of the drive transistor was taken to the 4 times the W by L of the drive transistor is shown in figure. This ratio of size was a typical ratio often chosen by NMOS circuit designers. The gate threshold voltage is seen to be 1.44 volts and the gain at the threshold voltage is minus 8.3. The output low voltage is 0.14 volts. This transfer curve is acceptable. NMOS logic dominated integrated circuit design during the late 70s. Indeed, it was NMOS technology that was key factor in the development of 8 and 10-bit microprocessors that enabled the home computation revolution in the early 1980s. CMOS logic, which will be described next, began to become more popular because its power dissipation was much less despite the fact that circuits took more area, the yield was less, and the processing was more complicated in the late 1990s. The NMOS logic was practically disappeared due to its power dissipation. However, was mentioned previously, similar logic families with similar design methodologies are still quite popular. Thank you.